automated building archetype generation through self-supervised learning for energy modeling. And for the paper, we have Xinwei Zhuang and her co-authors, and she's presenting. Come on over. Have the paper?
Thank you for the introduction. So I'm Xinwei, and I'm a fourth year already PhD student from UC Berkeley. Also, I'm a research assistant at Lawrence Berkeley National Lab. So I'll be presenting one of our most recent work, Encoding urban ecology. So we are basically proposing an automated tool for building archetype generation for energy modeling. So our motivation is that we know that building built environment has contributed significantly to the climate change and global warming. Within which the residential factor actually contributes over 1/3 of the carbon emission and energy consumption. So many efforts was made recently. Urban building energy modeling is actually a really recent field for research. So basically, people are trying to model the whole city with energy performance. So major contribution made by multiple national labs as well as some institutions such as MIT. So what is this urban building energy modeling? In one sentence, it's basically includes 4 parts. We have the model inputs where we collect the data from the whole city, and we propose some building archetype from the whole city. So for example, if we have 50,000 buildings, for instance, we can represent the whole city with 5 buildings. So that's the first step. And then we use simulation engines such as Energy Plus or some plugin for Reynolds to simulate the energy performance, and we do validation just to make sure it's not too far away from the real case, from the real world performance. And the last step would be visualization, analysis, and application. So what we are trying to contribute is the first part, the geometric part, because the current building archetype, they are kind of access to this question from an energy sector perspective. So they are not really considered, or they are not really concerned about the building morphology, which is what maybe considered the most intensively in architecture design and urban design. So just a summary for literature review, I guess there's only like 8 out of 30, so less than 1/3 that considers geometry into the building archetype generation process. And even if they do, this is how they include the geometry. So for example, on the left is a building archetype provided by DOE, Department of Energy. And they propose archetype for the whole United States, whereas we don't really see this kind of building in the real life, right? And on the left, there are several recent studies again that manually involve many manual decisions which building can be most representative, and they are designed specifically for maybe city or for district. So there are lots of manual effort to be made. In this, we call it big data era, there are lots of new tools for us to use. For example, on the left-hand side, it is CityGML, which is a universal language developed for city scale, so that everyone can contribute to this data set. And on the right is San Francisco Open Data Portal. So basically, we have lots of data at the urban scale for energy morphology. If we have the data, what are the tools? So that's where we contribute. That's a really long introduction. We propose this automated building archetype generation tool, and we have 3 objectives. We want to learn the latent feature given a building stock, and we want to automate the whole archetype generation process without any manual decision. And lastly, we want it to be scale invariant. So no matter you want it to be a local scale building archetype, or you want it to be a maybe archetype for the whole state, we can do that. So we choose a small neighborhood in San Francisco, which consists of over 2,000 residential housings, and with the footprint. And here's our methodology. The first step is through a neural network called the vector quantized autoencoder. It's a subset of generative models. So basically what it does is that we feed all the building footprint into this network, and the network can self-learn some latent space, some latent vector, we call it. And the latent vector is actually a largely reduced dimension of the building footprint, which is the image data. It's like 1/200 vector, and it can generate or reconstruct the building footprint from that latent vector, so that through this iterative space, we can relatively learn what a building footprint is just by 1/200 building, like 1/200 vector space. And we quantify our network's performance by either the validation or training loss plotted there, or we can just use visualization. Like we can input our original building footprint, and through 1/200 vector, we can just reconstruct it. We can just reconstruct the building footprint with like 200 digits. So that's kind of amazing. With that, what's really important to us is not the reconstruction purpose, but the latent vector space. So if we were going to visualize that space, it looks like that. So in the latent vector, it sort of self-organized into a shape that, for example, in this case, we have 5 clusters for that building stock, and each cluster kind of have some inherent or implicit features within them. Just to have a like detailed looking, yeah, I guess. Yeah. So for example, for each of the cluster space, we can sample from the latent space and generate some building energy models. And we can use that single building footprint to represent the whole kind of cluster. And for the sampling method, we propose two ways. One is to just sample from the center, and the other is to averaging the whole cluster within that building stock to get some imaginary averaging buildings. And we then do energy consumption analysis from generated building archetype. And so that's the equation. And you can see we actually performed pretty well compared to our baseline. So our baseline is the building archetype provided by DOE. Again, DOE provide a country level archetype that is maybe like if we don't have any other database, we'll be using that. So we are using that as baseline. They are pretty good, but again, they kind of construct the building archetype for the whole United States. So, you know, San Francisco is so different from Denver. So we need some local kind of specific building archetype, and that's what we are doing. We further extend our credibility to several other scales. And for each of the neighborhood, we follow the same kind of procedure. We cluster, we train the model, cluster within this within the latent space, and propose the corresponding building representative building footprint. And we again aggregate the energy consumption and get some energy performance for the whole neighborhood. And again, for every neighborhood we test, we performed like over 20% well compared to our baseline, the prototype provided by DOE. If you remember this chart, we currently only consider the building footprint as input data, which is not quite complete because what really affects energy consumption or energy performance is has other parameters such as vintage year, building program, etc. So in our follow like subsequent research, we propose MARL, so multi-scale archetype representation learning for urban building energy modeling, which we not only considers building archetype, building footprint, but also other metadata such as building height, building year, and building vintage. And this is also published on International Conference on Computer Vision. We published all our paper code and data. So if you're interested, you can have a look. Yeah, so I guess that's my presentation, just in quick summary, our contribution is as follows. So we firstly propose an automated process for the building archetype generation. And we use real-world geometry, so we largely increase the building archetype's resolution, and it's scale invariant, so meaning you can apply our method to a small neighborhood scale, or even a bigger district, or even a city scale. And again, lastly, our accuracy is largely improved compared to the baseline. So thank you.